Well, PCB, of course, really messed up soldering at a few points. This one probably turned out to be the best. Hello, everyone. Welcome to Big Electrode. Myself, Pratham Vora, and welcome to the very first part of our STM32 based drone project. So, in the beginning of the video, you saw this PCB. These are just the prototyping ones. Some of them have been damaged. As you can see, these all solder blocks. So I'll keep this aside and we'll just look at what we are working on right now. So just keep them aside. This is our main drone, and this is the discovery board of whose STLink I'll be using to program this STM32 C8T6 chip on the back, and this is the LoRa module. So let's take a closer look at our PCB. Alright, so before we get started, let me tell you, I'm very new to this thing, SMD and stuff, and not really an expert in soldering. So you can see I've ripped off some traces over here and here as well. It's for the MPU6050 chip, but I later decided to simply go with this MPU650 module. The chip on this module didn't respond correctly over here. I mean, it responds on the I2C addresses, but it won't initialize. So keeping this aside, now with the MOSFET things over here, these are the old MOSFETs, but it turned out that the drain of this thing, this both MOSFET internal is connected to each other. So even if I turn on one gate of one MOSFET, the other MOSFET will source or the other load will source its current through the MOSFET which is already turned on. So then this is what the MOSFET looks like. Let me just grab some of my tweezers. So that's how small the MOSFET is. And these are pretty commonly used on this TP4056 charging board, which we'll be using to charge our batteries, but that's adjacent to what our project is. So as you can see over here, it is. What I came up with the solution was, and I learned it the very hard way when just by turning one channel of one PWM channel of our STM32, both motors were spinning, so that was not really the best thing what we want. So I came up with this solution. As you can see, it's basically two of these small 8205A MOSFETs stacked on top of each other. It won't focus quite well, but I think that is manageable. And I snipped off the drain and the gate pin from the MOSFET which is on the bottom layer of the sandwich. It worked, but you say it's not really the best thing to do. Now I have to order MOSFET which is compatible with our voltage levels, and it is going to take some time. And doing this sandwich thing with these MOSFETs, I actually emptied the whole reel. So yeah, that's our progress so far on the PCB. The MPU6050 also had this interrupt pin, which I wasn't using because now I'll be using this module. I ended up soldering a button, push button for user interface and all, which came out to be pretty handy. The software on these things for driving the MPU6050 and the LoRa module is in progress. The MPU6050 is almost done. I'll be stacking this module and reconnecting with the PCB and showing you how the software is done. And it's written from scratch, and I'm using HAL for this purpose. The back side of the PCB is pretty simple. You have the SM32 C8T6, F103 C8T6, and for wireless we're using LoRa. I just had some of these modules lying around, but yeah, it's quite manageable to port it to other RF chips as well. Yeah, and for the programming part, as you can see, I have left out four pads. For two is for clock and data, and two is for ground and well VCC. And I'll be using my STM32 Discovery board's ST-Link. So yeah, it's quite huge. But yeah, this is the ST-Link circuitry, and I've disconnected the header, this header. So this chip is no longer connected to this particular ST-Link. And this is the headers through which I'll be programming our flight control. Yeah, so that's it. I'll be waiting for MOSFETs to come. By that time, I will be connecting this MPU6050 and showing you how the software is working and all, and the I2C connections. So this is the datasheet for MOSFET we have used in our design, and I think it's pretty clear from the start the drains of these two MOSFET inside the same chip is connected to each other. I don't know how this thing didn't caught my attention, but yeah, that's a fatal mistake anyway. To fix this problem, I think I have found the MOSFET which is compatible. It's this SI2302 CDS from Vicious Siliconics, and this thing has lower gate to source voltage. I did try it with some beefier MOSFETs early on to get some work around, and I can start the project faster. But yeah, I have to order this thing, and to get it soldered on something like this. So this is a piece of our perf board, the dotted PCB. I'll be soldering. I'll be using two of these thing on either sides of the motors, and the MOSFET will be placed on this PCB board. And yeah, these are compatible anyway. I mean, it's only a three-leg device, shouldn't be a problem. So this is how our drone looks when it is all assembled. The wiring on this thing is done using enamel copper wires. So these are just little strands of wire you must be seeing here going in the PCB board. So trust me when I say that I did try to record the whole process in time lapse, but the phone glitched and the recording wasn't saved. This is the MPU650 module on top of it, and if I show you one of our blank PCBs, the module is directly on this footprint, and these are the SCL and SGA connections near R13 and R12. Yeah, so this SCL and SGA connection on this module, which is this and this, also are going downward beneath the module, and it is secured using double-sided adhesives. So yeah, it's holding pretty good. So yeah, now let's just hop into our computer and see how the software works, and I'll show you a few things. Hi, so I hope it's a little bit better right now. We have a drone right here, and we'll be connecting our drone to a PC through this uh, UART serial converter thing. We have a debug port right over here along with a serial port connection. I hope I showed it to you guys. So I don't really have the tweezers right now. So these two pins over here, these two pins are the for the UART. It goes underneath the PCB and connects to the UART pins. I didn't really added it in the schematics, but that's fine. We'll correct it in our next revision. So let's just connect it real quick, and let's just hop onto a screen and see what the graphs are and how it works. Okay, so now we have connected it. As you can see, it's connected right now. And right after powering it up, it will start the calibration process. So it's better we don't move the drone too much, otherwise the calibration goes off the charts. So it's not really possible to fit everything in the whole frame. So let's just connect it. Okay. So as you can see, right after connecting the drone, the LED is blinking, which is for the calibration process. It is an indication, and once the calibration has been completed, the white LED glows up, which indicates that it is completed. Now you can move it freely as you want. So let's just see what the graphs are. Okay, so the application that we'll be using for demonstration is the stereo oscilloscope application. It's not really stable for now, but it works. As soon as I connect my serial port from this option, you can see all the accelerometer and the gyroscope reading. We'll look at the channel 1 to 3 and channel 4 to 6, sorry 3 to 6 for our accelerometer reading. This is for the accelerometer one, this is for the gyroscope one. So if I move drone in only in the yaw direction, as you can see, the blue line indicates the yaw. If I keep it on the table, it's more stable. This one is for the roll angle or the x value of the gyroscope on the x-axis. So if I move it only in the roll, you can see the red line going straight up and straight down, which indicates the rate of change in angle in the roll axis, and this is for a pitch. So as you can see, it works and it works flawlessly. If I keep the drone pretty stable, as you can see, all the values are almost zero. It's not quite zero, it's something around 0. Minus 0.2 and things between. Now let's just look at the accelerometer now. So the blue line is for the yaw acceleration, which is 10. Obviously we have the gravity working against it, and if I just tilt it a little, you can see the blue one drops. I will just increase it for now. I hope it works. So if I tilt it, you can see the blue or the z-axis drops, uh, the yaw angle. Similarly, if I tip it right like this, the pitch angle is facing downwards. We can see this red line going negative. If I do it like this, it's for the accelerometers. Hope you guys find it helpful. Now we'll look at the code of how we are doing the calibration and how we are communicating it over I2C. Hi, so welcome to the source code. As you can see, it's an MPU6050 library which we have made, and there are functions we have to call so that we can get the gyroscope and accelerometer working. We first have to self-test the MPU6050. Now this is not really required for the most part, but it is done to make sure that the gyroscope or the chip we are using isn't faulty or anything. During the time of production, there are some calibration values which are already fitted into the MPU6050 gyroscope chip, and by doing this test we can ensure that the deviation from the calibrated values are under range. So let's just first have a look at the code. We first have to read this register. As you can see, this register contains value self-test values, as I say, for gyroscope and accelerometer, which we have to extract and bit shift it so that we can get the exact values for accelerometer and the gyroscope. Start by finding the factory calibrated values using this particular formula. So before we do it, this is how the self-test calibration works. We first find the self-test values and subtract it with the factory test values and divide it by the factory test, obviously, so we can get the percentage amount which has been deviated from the factory calibrated values. And if it is under the range which is acceptable for us, we can render the part as good or it is faulty. Once we have done with the self-test values, we have to initialize our MPU6050 gyroscope, and this is done over here. So now these are the registers, UMI, power management, configuration, so on and so forth, which are given in the register map. So as you can see, it's a register which directly has the value of our address we are communicating with. Next we go towards the power management register. So this is the power management register. We first have to set the clock select bit over here. So here we are setting the value 1, which stands for PLL x-axis gyroscope reference. Next we have the configuration register. So in the configuration register, it has the low pass filter settings. Now for people who don't know what exactly is low pass filter, let me explain it real quick. Our accelerometer and gyroscope reading, it will change pretty fast, but we don't really want that fast changes, which stand for high frequency changes, so that our drone behaves in a proper way. It is not jerking around. Setting the DLP values over here, we can select what the bandwidth we want and the amount of delay it will cause in the gyroscope output. Now here we have the gyroscope and accelerometer configurations. Let's have a look at those registers. So now we are here at the accelerometer configuration. Over here we can set what the full scale range we want. For the accelerometer we are setting it to 0, for the gyroscope we are setting it to 8, which means that it's plus minus 2G. The 0 cross 8 simply corresponds to 500 degrees per second. Next we have the signal path reset. Now this register simply resets the gyroscope and accelerometer register output. Now the most important part in all this is calibration. So we have to calibrate our gyroscope first. In the calibration function, as you can see, we first start by reading our gyroscope measurements from this particular register, gyroscope x out h. We divide and get the degrees per second answer, and we keep adding it 4000 times. Now once it has been added, we we take an average. Basically the average value which we have got is value when the drone is not moving, and so it's the net zero value for us. We store the calibration value in this calibration data structure, and in the get gyro or get accelerometer function we subtract it. So for the accelerometer we don't really have to calibrate it, it's fine, but in the get gyro, as you can see, we are subtracting it. That's how our gyroscope code works overall. Alright everyone, that's it from my side. Thanks for watching. Subscribe to the channel. If you have any suggestions, comment it down below, and I'll see you next time.